Okay, hi guys. So in this lecture as well, we'll be continuing on seeing equilibrium constants for gaseous reactions. So in the previous lecture, we discussed about Kp and Kc. Kp is the equilibrium constant in terms of pressure. Kc is equilibrium constant in terms of concentration. Now we'll see another type of equilibrium constant in terms of mole fraction of gaseous, which we call it as Kx. So Kx mole fraction of C raised to the power C, mole fraction of D raised to the power stoichiometric coefficient of D. Similarly, for A and B, we write the same. So where x, any x D, let's suppose, is mole fraction of D in the reaction mixture containing all the four gases. Okay, so now for an ideal gas A, we can write that ideal gas A, we can write that PAV equals to nRT. Okay, and Pa is nothing but moles of A divided by V into RT, just rearranging the above equation. Okay, which is nothing but Na by V is molarity or the concentration of gas A, RT. So we can write Pa as concentration of gas A times RT. Let's say it equation number 1. Now similarly, we can say that the partial pressure of gas A is equals to mole fraction of A multiplied with total pressure of gaseous mixture. Okay, so or in other terms we can write that Pa would be equals to mole fraction of A times total pressure. Okay, so now let us actually derive, just remember these two equations. So now let us derive some relation between Kp and Kc, which is the equilibrium constant in terms of pressure for gases, and Kc is equilibrium constant for gases in terms of concentration. Let's derive some relation between Kp and Kc. So we know that Kp is partial pressure of C raised to power stoichiometric coefficient of C, similarly for all the other gases. Okay, and we know that Pa would be equals to concentration of A multiplied with RT. So just putting this value into the equation for all the gases, so we will be getting Kp as would be concentration of C raised to power C RT raised to power C multiplied with concentration of D raised to power D RT raised to power D again, similarly divided by concentration of A raised to power A RT raised to power A multiplied with concentration of B raised to power B into RT raised to power B again. Okay, so we can write that Kp would be equals to, so let me do some pre-processing here as here only. So it would be concentration of C raised to power C multiplied with concentration of D raised to power D divided by concentration of A raised to power A multiplied with concentration of B raised to power B multiplied with RT raised to the power this is C D minus A plus B, so it would be C plus D minus A plus B. Okay, so we can write, we can see that this term is nothing but Kc and multiplied with RT to the power C plus D minus A plus B. Okay, so Kp can be written as Kc multiplied with RT delta Ng, okay, where delta Ng can be written as C plus D minus A plus B. Okay, so delta, or in other terms you can say that delta Ng is the moles of gaseous products minus moles of gaseous reactants. Moles of gaseous products minus moles of gaseous reactants. Okay, let's see some examples now. So we have N2G plus 3H2G forming 2 moles of ammonia. So delta Ng we have to calculate for this reaction. That would be moles of reactants, which would be 2, minus moles of products, which would be 1 plus 3. Delta Ng would be minus 2. Okay, so Kp, relation between Kp and Kc would be Kp equals to Kc RT to the power minus 2. Okay, so please note that delta Ng can be positive, negative if the reaction positive or negative or 0 as well. Positive, negative or 0, all the 3 cases would be there. Okay, so let's see another example where we have 2 moles of SO3 gas converting into 2SO2G plus O2G. So in this case delta Ng would be 2 plus 1 minus 2, which would be 1. Okay, and next we have carbon monoxide reacting with half moles of oxygen converting into carbon dioxide. So delta Ng in this reaction would be minus half. Similarly, let's see one more example. COCO3 in solid state getting converted into calcium oxide plus CO2 gas. So in this case as well delta Ng would be 1. Okay, and why would the delta Ng 1? Because delta Ng is moles of gaseous products. Gaseous product is only one in this case, and there is no gaseous reactant. Okay, so moles of gaseous reactant would be 0, hence delta Ng would be 1 minus 0, which would be 1. Okay, so with this we come to the end of this lecture. In the next lecture we'll be continuing on seeing more on Kp, Kc and delta Ng. Till then, good luck and goodbye.